done by the system, and it gives the kinetic, it gives the internal energy of the system of inverse, right? And the work done is given by this integral here, PdV, which is equal to the area under the curve in the PV diagram here. So this is some arbitrary PV diagram that I just draw, right? And if you do this integration, the work done is just this area. Okay. You're welcome to take the lecture or take pictures. I don't mind because I myself I'm a very slow writer. I don't take very good notes. Let's see, any question this far? This is all clear, right? Simple, straightforward. In most gas system, two variables is enough to define a system, right? Two independent variables. And in this case, I choose temperature and volume. Okay? And then specific heat, or actually heat capacity, is defined as the heat transfer that you need to change the temperature by 1 degree, right? And there are two kind of heat capacity or specific heat here. One of them, the two famous one, you can define many other things, is constant volume, right? And constant pressure, right? Okay. And this is important in many ways, and we'll discuss later on. But from this we derive that equation, right? After a long steps in arithmetic and algebra, right? We get that, and this is from note from last Wednesday. Okay. So the difference is equal to the partial of U with respect to B plus the pressure times this times dV dt. And so there are two parts here, and this is a very important equation in many ways. But just looking at it from one direction, from kinetic theory, you know for ideal gas, right? This is all from kinetic theory. You can do this approach completely from thermodynamics. That's later. We know from kinetic theory because let's see, at least for monoatomic, you know that U is equal to 3/2 NKT, right? Okay. So U is actually not is an independent function of volume, right? So dU/dV is equal to 0. Okay. So then the difference in the specific heat is only the second term, right? That comes from the expansion, right? So, and if you actually do the math, then this is equal to Cp minus Cv is equal to pressure times dV dt at constant pressure, and we know from the equation of state, from PV equal NKT, right? The derivative of a volume with respect to temperature is just NK over P, right? And combining these two equations, you get Cp is equal to Cv plus NK. Right? And this is always true for ideal gas. Okay? Mainly because this term is 0.
So the bottom one is only true for ideal gas, and the top one is true for all gases?
Yeah, this is true for everything. Right? This is true for all gases. Right? And in fact, it says that for all gases, the difference between the specific heat has two components. One of them that comes from the expansion, right? The difference is that when you do it at constant pressure, then the gas expands, and then you drink water, right? So it has more heat capacity. Whatever you put in, some of it goes to the internal energy of the system, some get used to expand the gas, right? But there's another term to it. What happened is that as you change the volume, right? If for some reason the energy changes, right, then you have a difference in the heat capacity also. Okay? And this you will see in other gases. Real gases have that issue, right? Van der Waals gas, for example. Right? And if you look at the Van der Waals equation, you can derive this and you will find that this is not 0.
What's the, I guess, practical significance of having an expression for Cp minus Cv?
Good question. A lot of reasons. In the discussion you'll see it in chapter 20, in the discussion of entropy, and the, let's see, I'll go into it later on, but it's almost, one way to see it is almost like if you're going from the direction of thermodynamics, you almost see it as a definition of what ideal gas is, right? So you measure this, right? If you measure this for gas, right? If you find that from the result of your measurement, right, that this is actually independent of that, right? Then you can always approach it from a thermodynamic point of view, forget kinetic theory. That's a definition of ideal gas. That energy is not a function of volume, right? So this is important because this is used to actually compare your understanding of thermodynamics with experiment. That's a very good question.
So why were you able to take out v in the function for u?
Take out v in the function for u.
Because you were like u of vt equals u of t.
Yes, because I was, we are trying to do it from many directions, right? I mean, I'm not striving for an a priori discussion of thermodynamics, just making sure that everything is self-consistent. You know from kinetic theory, U is 3/2 mkT, right? There is no volume in it, right? So U is independent of volume from kinetic theory, right? Assuming all those properties of molecules and ideal gas that we discussed. Okay. Let's see. So yeah, for ideal gas, this is what you have. Okay, and you also know this is just an expression for an exact differential. There's a lot of confusion about this from Wednesday. This is no more than just that statement. We discuss this. If this is not clear, we can talk about it again later. We'll always come back to the same thing again and again, by the way. And that's the way we do physics. And for ideal gas, right, because this is 0, then you have that. Right, because this term is 0. Only for ideal gas. Right? So this gives you U, since this is just the specific heat, right? Where was that? Oh, I didn't do it. Did I do it? Did I miss something? I didn't write down. This is equal. If you do this, right? I just wrote Cp minus Cv, but I forgot to write Cp is du dt at constant volume. Right? So this du becomes just Cv. This is what we guess. It's not true for other things. Right? Quantum answer is not true. Questions so far? Okay. And just as an aside, not an aside, just to complete the discussion, for monoatomic, this is all just ideal gas, but for monoatomic, let me just write it. Ideal gas. And Cp is 3/2 mkT, right? Okay. And we discussed this a little bit. We also know from kinetic theory or statistical mechanics, this is one of the things that I said that you should remember for the rest of your life. This is the equipartition theorem. degrees of freedom. Average thermal energy right? And because my system here, the gas, as usual, the gas of piston or whatever, has n particle in there, because the three dimension has 3 degrees of freedom for its kinetic energy, then you have 3n. Okay. And each get half kT, right? Therefore U is 3/2 kT. Okay. And we'll discuss diatomic gas at the end of lecture. But let me move on. Oh, I should erase this. The other one first. Okay. One thing that I want to clarify is that you can define things that the independent variable is temperature and volume, right? But you can also do same. You can also do pressure and volume. And this is done often, in a PV diagram. You draw things sort of like that. And for ideal gas, V equal mkB, which is the equation of state, you have an isotope, right? You have a curve that looks like that. I'm not very good drawing a graph. Okay, so this is T1, T2, T3. This is called isotherm. So each of these curves has an expression E equal to N K Ti over V. Okay. For every Ti, the dependence of pressure and over volume is called an isotope. And this is no more than an expression, a graphical expression of the equation of state. Right? The reason I want to emphasize this is because we want to go into thermodynamic processes. It has nothing to do with this curve. Right? Okay. So also we did this on Wednesday. Right? Since now we know a little bit about the machinery of the first law, we want to look at an isothermal expansion. Gas in a piston, right? Call it system S, has a pressure P, right? And the whole thing is inside a bath of temperature T, and you let the whole thing expand, right? And when you do that, right? So if I draw it on a PV curve, right? So this is the isotherm of the temperature T, right? This is just an isotherm, but it just so happened for isothermal expansion, right? The process is happening along isotherm. Right. It's only true for isothermal expansion. Right? It's not true for any other thing. But that's always true. For ideal gas, it's always true. Isotherm is given by that, right? So I'm drawing one of our X curve, and that's just the isotherm. Okay? And the work done is, of course, this area underneath that, right? Okay? And the temperature change is 0. But it's isothermal. If I can guess. Then what you have is du is equal to 0, right? Because there is no change in temperature. And in that case, from the first law, we know that du is equal to dq minus dw, right? So this gives you that dw is equal to what? dq is equal to dw. And we found also from last Wednesday, just to summarize, I don't have to do this again, that the work done here in the expansion is given by nkt log of the final over the initial. Right? And then the work that the gas is doing, right, comes at the expense of the heat transfer coming into the system. Right? The internal energy of the gas stays the same. This thing expands, it sucks in heat from the heat bath. And we assume that the heat bath is infinite, so nothing changes. Okay. Is this clear?
In the book, it talks about how it proceeded like a quasi-static, like really slowly. So then why does it matter if it goes fast or not?
It does. And then maybe can we postpone this discussion until Monday? I want to lump it together with the discussion of entropy.
Okay.
Right. But it's a very important question. There is all this thing that I just completely overlook and stuff under the rug, the concept of quasi-static and concept of reversibility. We haven't discussed that. That's actually really important. Right? And in this case, to answer shortly, is that if things are not done slowly, this is vacuum, right? Suppose this is vacuum, right? So there is no force holding it back. That this thing will just, has an infinite acceleration, right? Or not infinite, depends on the mass of the piston, right? So it moves very fast. And what happens is that you get turbulences. Right? Pressure is not a very defined concept anymore. We want to make sure in the process of going along the diameter that every point is well defined. Right? And if you just move this very fast, then what you're doing is, you go to some unknown path to reach its final configuration. Yeah.
Would our work also change that?
Sorry?
Would our work also
Yes, then everything changes. Then all this calculation is wrong. Of course, real engine, you cannot do that, right? This is a theoretical discussion, by the way. Right? Almost like your frictionless state. Right? But this is necessary to be able to actually calculate. You have to ensure that the process is going to come all along the curve. Right? There's no turbulences. Turbulences can be energy. Right? Okay, so that we did. That's the information content. Oh, but another question, please. But you have a question first, right? No.
So I think the differential for quarks is exact. I mean, it is an exact differential.
Where? Oh, yes, it is. Yeah.
What is the ln of df of
Oh, this I actually derived this in class on Wednesday. Right? So if you go integral of p m k t dv over v, right, from v initial to v final. This is definite integral of 1 over x, right, to v log x. This is from calculus. And then the next thing we did was another important process. It's important in the sense of the theoretical discussion of thermodynamics. Okay? Is the adiabatic expansion of a gas. So in this case, instead of having the system inside the heat bath, you actually isolate the system. And system S, no heat transfer. Right? In this case, TQ is 0 always. Right? That's the definition of adiabatic. It's not the exact meaning of the word though. Right? And then you do this expansion. There's a pressure here, and the gas expands. Okay? And we want to know, the heat, how much work done that you do in moving, say, from the initial to the final, right? So this initial is over here, and finally we have something over here, right? So, and this is originally the temperature T. Okay, since TQ is 0, I'm always facing forward if I'm doing a lot of math. Just interrupt me anytime if you have any question. So, in that case, then from first law, we know that U is just equal to minus CW, right? Okay, this is his first law. Okay. And from ideal gas, we also know, I'm just redoing this. I did this already on Wednesday, by the way. But it is so important, let's just do it again. CVP is then equal to minus VP. Okay. I'm just giving some stuff. This is equal to, I can express P, this P equal to NKE. Right, and I can write this as minus NKE over 3, right? Is that correct? Yes. And regrouping the terms, I have dt over t is equal to minus nk over cv times dt. This is physically this is what happened. This is just the first law. Okay, the rest is just math. Okay. And we already did this on Wednesday. We found that from integrating this differential equation, you get TV gamma minus 1. By the way, gamma is defined as Cp minus Cp. And of course, you know why in gas Cp is equal to Cp plus NK. Okay? We found that T times volume to the power of gamma minus 1 is equal to constant. Right? Or if you like, you can also express it as T initial. T initial to the gamma minus 1 is equal to T final. Right? T final gamma minus 1. Okay? Also, since PV is equal to NKE, right, then you substitute T equal to PV over NK in this equation, right? Then you get from this and that, you get PV gamma equal constant. So use whichever one is appropriate for the problem at hand, right? Sometimes in the textbook it's written like, more often it's written like this, but this is equally valid, right? Depending on the problem that you're trying to solve. So, how does this look on a PV diagram, right? So you do initial division. So suppose you start over here at some P, V initial, I initial, V initial, and temperature initial, right? And they are related by division of state, right? And it goes to some, so this is an isotherm for it. adiabatic expansion satisfies this equation. So in that process, just like in the isothermal expansion, right? In that process, we veer away from the isotherm in this case, because gamma is greater than 1 by definition, almost by definition. Right? Cp is equal to Cp plus Nk, right? Then this actually go like that. Right? Let me just exaggerate this a little bit. The isotherm goes like that. This is P final, P final, P final. Also related by the equation of state, right? And this is the process. This is the curve PV gamma equal constant. Right? And there is another isotherm. Okay. This is isotherm at temperature Tf. Okay. And the work done is just, of course, we're doing expansion here, right? The work done is just area under this curve. Okay. So we want to calculate that. Questions so far?
Might be belaboring a dead point, but if dq is 0 and du is equal to minus dw,
Yeah.
how does it remain like an uncertain? Because it's not the sum or subtraction of them anymore.
Yes. You mean the slash?
Yeah,
I'm just formally narrating it. But you're right. And
it has to become multiplied.
right, yes. Right.
Why do we put gamma minus 1 on?
Gamma minus 1. Oh, here?
Yeah.
Oh, this I did.
Gamma.
This we did on Wednesday.
Okay,
So yeah, go back to the note. It should be there, right? If you solve this equation, this is the equation that matters. This is the physics, right? The physics come from the first law. Right? dt over t is equal to minus nk over cv times dv over v. Right? And basically that term here, this term here is gamma minus 1. It's equal to
Just conceptually,
Yeah.
so for adiabatic expansion, does it just mean that like a gas is expanding too quickly for heat to?
yes. You can approximate that way, right? Many processes in engines, say, right? If the whole expansion happens very fast, right? As long as you don't worry about, quasi-static condition and reversibility condition, right? Suppose that's respected. If this thing expands so fast, there is no heat transfer, right? Then the expansion can come at the expense of the lowering of the internal energy. Okay? So this is say important in homework number 2. One of the question is one of the difficult questions in that homework is you will solve adiabatic atmosphere. We did isothermal atmosphere in class, right? But you will do adiabatic atmosphere in the homework. Also, it's very important for sound propagation. When you do sound propagation, because the sound is just an oscillation of an expansion of gas in air, and it's happening so quickly, right? There's no time for heat transfer to happen. And it's also this sound. This is very important. In fact, the gamma is there all the time. First.
So when you're saying like adiabatic expansion is going too fast for heat transfer to occur,
Yes.
does that
In
mean-
real life, in real experiment, right? Here, of course, this is completely theoretical.
Right. Does that mean that adiabatic processes are like necessarily irreversible?
No, that's not true.
Oh.
I mean, it's all a matter of time scale, right? In this discussion, this is this is actually done in a way that's actually reversible. So you can always go back and forth. You can go that way, and you can go this way. Right? So it's completely reversible. Because you're doing it along this curve without veering away. At every part of the process, everything is well defined. Right? So what happened in reality is that there's a pressure here that's pushing the piston away at the expense of the energy. Right? But you're holding it so that this thing is actually moving very slowly. So you're pushing against the pressure. Right? Basically, you're pushing it with almost equal pressure. So this thing moves differentially very slowly in time.
Okay.
Did I answer your question?
Well, if you're moving like differentially slowly, then wouldn't you have time for the transfer?
Oh, no, but then here I'm just putting the whole thing in an insulating box.
Okay.
Right, there is no heat transfer. But what I need to know all your name at some point. Imad. What Imad was saying is that this is a good approximation to those processes that happen so fast, right? There is no time for heat transfer to happen.
Okay.
It's a physical approximation, right? This is a theoretical discussion.
Right.
Right.
So those processes would be irreversible.
Yes. It's an approximation, yeah. But, a lot of processes, most of them are reversible.
So when you say adiabatic, do you essentially just mean that there's temperature change rather than like isothermal, or there's no?
Yeah,
temperature
well,
change?
no, in this case, no. Adiabatic means no heat transfer.
Okay, that's what you're referring to. Okay, adiabatic.
Yeah.
So there will be pressure, temperature, volume change,
Right, yes.
and this means there's no heat transfer. Whereas in isothermal, there could be heat
There
transfer.
could be heat transfer.
Okay, thank you.
What is an example of a process that's not reversible?
Next example. Okay, any question? Is that clear? Okay. So let's see, back to adiabatic expansion, we want to calculate the work done, right? Along this curve. It's not that easy because it has this equation here, there's a gamma on it, right? Kind of complicated. But we know that TW is equal to minus TU, right? Right? So W, the total work, I don't know what the original jet is, right? This is formal convention, it's always W. So initial to final, then it's equal to minus initial to final TU. Okay? Right? I haven't done anything yet, this is just first law with no heat transfer, right? But we know that U is a state function. Right? Therefore, this integral, right, is only a function of the energy at the final division minus the energy at the initial division. This is just U F minus U. Right? So the total work done then is just equal to Ui minus Ui. And you just have to do some algebra, right? Yeah. You just have to do some algebra because actually it turns out you do it. For whatever reason, these guys too tired last night. Because U is equal to 3/2 mkp, right? For monoatomic ideal gas in this case, right? So gamma is like gamma is equal to 1.4. If you do this right. Then from this equation, sorry. We know the equation of state is equal mk, right? and we know PV gamma is equal to constant. Right? This equation is enough for you to find PI if you're given all the right variables, PI, and then P final, or a combination of 3 out of 4, then you can always find PI in PF. Okay? Given 3 of those variables, I can always find this point, and I can find that point. And I can throw the isotope. And I can throw this, right? And knowing the temperature, if I know Ti, and I know the final, right? Then I can use it to calculate the energy. That's all I'm saying, right? I didn't want to write it as a formula, right? There is another formula to remember. But you should understand physically what happened is that I have an equation of state, I have the process, right? From these 2 equations, it's enough for me to define everything, right? To find out about everything, in particular the temperature, right? Right? And from the temperature, I can calculate the energy. And from the energy difference, I can calculate the work. Right? Because all the work done by the system comes from at the expense of the energy of the gas. Is this clear? Is this boring? This will be interesting when, there is a reason for all this. It's not for nothing. And it will become clear in chapter 20 when we talk about the second one. Okay. Back to Victor's question about the non-reversible process. So we did 2 processes, right? Isothermal. One, and number 2, adiabatic. The third example I want to talk about is a free expansion. I did mention that one of your homework problems will be on adiabatic atmosphere, right? Free expansion. Like this, yes. Okay. So, just to stay close to how the original experiment was being done, this is actually also called Joule expansion. And it's actually one of the more, it's a very simple experiment, but it's one of the more important experiments in the history of classical thermodynamics. So what you have is you have a system, right, with a partition. So all the gas are over here, as in these vacuums. Okay. And the whole thing is sitting inside a bag. But in this case, it's actually a finite bath. And in reality, there is no such thing as infinite bath, right? But this is done in such a way that you don't have to worry about the heat transfer going into the system, right? So that the whole thing is happening fast enough that I don't have to, as you said, it's still not the same. The whole thing is happening fast enough that I don't have to worry about heat transfer between the bath to the atmosphere, to the outside environment. But I have to worry about heat transfer between the bath and the system. Okay, meaning that the bath is small enough, relatively of equal size in the system. Okay, so there is T here. Okay, at temperature T. Okay, so what we do is at some point, well, in the real experiment, you try to track it, but conceptually, what happens if you make a small hole? Right? And gas start to leak, right? It escapes to the other compartment, right? Without any resistance, right? So, you do molecules here, it's just diffusing in that direction, right? Into vacuum, right? And eventually, this is the initial state. In the final state, what you have that will be equal pressure, right? So gas will flow that way, it will flow this way, everything will be in equilibrium. Okay? So, now what happened here? First of all, is this reversible or non-reversible? Can I erase something? Can I erase? Let me erase that. I mean, it's really reversible. Like, what's the definition of reversible? I mean, we haven't really talked about it that much, but the whole thing started over here, right? And then over time, it's uniformly distributed in the two compartments. And it's, intuitively you can say, well, it's not reversible because, I mean, it will never happen again that this thing is going to all move, you can never go that, right? Just intuitively, right? I mean, it's a big philosophical or theoretical question as to why not. Right? I mean, in theory, if you actually reverse time, right? If you take a movie of this process, like what C is doing, right? And then you play it backward, right? Then you have something that started as an equal distribution between the two compartments, and then as the time go forward, suddenly everything become, everything move to the left compartment, right? So why is it not happening like that? It's a big question. Okay, it's a question that you have to solve when you do statistical mechanics. But it never happened, right? And in practice or in reality, it never happened, right? Therefore, it's not reversible. So what happened here? So here in this case, what happened? This is what John did, right? First of all, there is no gravity, right? There is no work done. The gas is just escaping with the other compartments. Is it 10 o'clock? 1 minute now? Let's start again on Monday. I'm almost there.